All right. Hello, class. Welcome back to lecture 16, part B. Part A actually went a little bit longer than I intended it to go, but hopefully it's all for the best. In this lecture, we're going to talk about or focus on that question of, right, how to enforce positivity of a polynomial for everywhere, basically. In the next lecture, we'll talk about on local sets, but in this lecture, we're focusing on global positivity. And actually, the answer to this, or the answer we propose, is relatively simple. However, I will try and make it complex by talking about it or motivating it in several different ways. Hopefully, one of them will click with you and make sense. Okay, so let's talk about it in one way, which is sort of thinking of it as a Lyapunov function, right? So what do Lyapunov functions look like? What do they look like? Well, we know for, of course, quadratic Lyapunov functions, they look like x transpose p of x. But let's think about them in general, right? And why they look like that, and why we're enforcing positivity using positive matrices and so forth. Right. So first of all, right, the Lyapunov function has to satisfy certain properties, has to be positive. 0 at the equilibrium, or that actually we can relax that, but let's not deal with that at the moment. Okay, so it has to be positive. And it has to be negative on the trajectory, so v dot has to be less than 0. V is greater than 0. That's what I said right there. And then v dot has to be negative. And where does that v dot negative come from? Well, if you remember what the Lyapunov function represents, it represents a metric on h, for example, on the solution map, right? Starting from that initial condition going forward in time, right? And so obviously, if the size of the solution and metrics are positive, right? So it's a measure of size. If that solution is decreasing as we move along, right? And so the size of your solution has to decrease because, right, you're cutting off pieces of time from it, right? No matter what the solution looks like, if you cut off this piece, it's going to be smaller than this piece, than the whole piece, right? So it has to be decreasing in time. And in fact, one very common form of Lyapunov function, the way we like to think about it, is that one we sort of got from the linear case, which is just the integral of the trajectory. And so if we talk about the trajectory now, well, we don't have the solution explicitly, or e to the atx. We do, however, have this solution map, and so we can, the obvious generalization of the standard converse Lyapunov theorem for linear systems, right, is just to take this metric to be the L2 norm, right? And then we have the Lyapunov function is actually just the square integral of g of x, comma t, dt squared from 0 to infinity, right? So that's the obvious Lyapunov function. And actually, this Lyapunov function is used, it's a Massera converse Lyapunov function. I give some credit to Massera, all these mathematicians. And it's often used to prove existence of Lyapunov functions. We know that the solution map exists, and therefore we can prove that the Lyapunov function exists. We're not going to focus on that too much, other than focusing on the parallels between the linear case and the nonlinear case. So specifically, right, the Lyapunov function having a representation in terms of the square, g comma t transpose g of x comma t. Right. So having the squared representation of the Lyapunov function, and there's an integral in there, of course, we have to get rid of time. But in x, it has this sort of pseudo-quadratic form, but of course, this is not linear in the nonlinear case. It's a nonlinear function in the nonlinear systems case. However, maybe we can still do something with this. So maybe if we say assume that the function is separable, then we can integrate off time in the middle, and the Lyapunov function suddenly looks like some kind of square. So let's take this this analog to the linear case and see where we can go with this, right? So in particular, for linear systems, we can restrict ourselves. We can parameterize all possible Lyapunov functions using quadratic Lyapunov functions. Is it possible in the nonlinear case to also parameterize all nonlinear Lyapunov functions or non-quadratic Lyapunov functions using some kind of similar representation? So the important part is all Lyapunov functions can be represented using a quadratic form in the linear case. Necessary and sufficient conditions. There are exceptions to that, of course, like there are exceptions to everything, but mostly for the systems that we've considered, they're necessary and sufficient. So let's go to the linear case and think about how what all Lyapunov functions look like. Right? So in the linear case, right, we're looking for a positive matrix, P greater than or equal to 0, where P represents a Lyapunov function of the form X transpose Px. And in the linear system case, we know that a necessary and sufficient condition for a quadratic Lyapunov function to be positive, semi-definite, is for the matrix P itself to be positive, semi-definite. And actually, in the linear case, the representation is unique for a given quadratic Lyapunov functions. In any case, in the linear case, we have these 15 parameters, right? 15 elements, unique elements of P. And if P is positive, then we know that the quadratic Lyapunov function is positive. And why is that? Well, I mean, we could just say the definition of positivity of a matrix, but let's go a little bit deeper than that, right? So if P is positive, well, then we know that P has a square root, so Q transpose Q. And then the Lyapunov function itself can be decomposed as X transpose Qx equals just the square norm of Qx, square 2 norm of Qx. So if we now think about this Q as the matrix exponential, what happens, say, for example, if we generalize this Qx to, say, nonlinear forms, g of x, for example? Well, can we parameterize non-quadratic Lyapunov functions using that approach? And so the obvious generalization then of these quadratic Lyapunov functions, nonlinear systems, right, is we take exactly the same form, the same quadratic form, but on the left and the right, we replace the just x1 to x5 with higher degree forms, right? So remember, this was representing Qx, Q comes here and the x comes here, right? Now we want to generalize this to squares which are slightly more complex, g of x, right? So in this case, right, if we make g equal to a polynomial, for example, then we can represent it as C transpose x, or sorry, not C transpose x, C transpose ZD of x, right? And so it makes sense then to think of our Lyapunov function in the nonlinear case, v of x, and here we have two variables, so x comma y, as g of x transpose g of x, and bring that representation down, zd of x transpose c transpose, or actually the c doesn't get transposed, cc transpose zd of x. And here actually let's use this matrix here, q, 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 right? So this is a sufficient condition, at least in this case, because matrices have square roots, for positivity of this class of Lyapunov functions, and it makes sense that our Lyapunov functions would look like this, right? So if we assume that our Lyapunov function looks like this, then we can simply impose positivity of this matrix, and that gives us a sufficient condition, at least, for positivity of the Lyapunov function itself. And conveniently, of course, it allows for this representation of the Lyapunov function using, again, these 15 parameters. Now, is this, of course, I mean, this makes sense. We've motivated it for Lyapunov functions, and then the question is it true in a broader sense? Do arbitrary polynomials have pseudo-quadratic forms? I say pseudo-quadratic because, right, this is not linear, right? Quadratic would have a linear term on the left and the right. And these have nonlinear terms on the left and right. But it's pseudo-quadratic. Let's call it pseudo-quadratic. So pseudo-quadratic Lyapunov functions. Are pseudo-quadratic Lyapunov functions necessary and sufficient for stability? Well, actually, it turns out that they, again, right, referencing some old papers of mine, you can prove, actually, that pseudo-quadratic Lyapunov functions are necessary and sufficient for stability of certain classes of polynomial systems. So this sort of motivates our pseudo-quadratic representation, or our positivity condition here. That's one motivation for it. Let's decompose what we saw in that previous slide a little bit. I think about it a little bit. So what we've done basically in that previous slide is we said that the Lyapunov function v is positive if it has a pseudo-quadratic representation for some positive matrix P. Right? Pseudo-quadratic Lyapunov function. And then the reasoning, right, that this is a positive Lyapunov function is P is a positive matrix, and therefore it has a square root. It has a square root. We can write as Q transpose Q. Right? And then if we plug Q transpose Q into the Lyapunov function, just bring that P down to Q transpose Q, then as in the linear case, we can separate this, right? This in terms of QZ of x, right? Which takes the place of the e to the atx. Well, the integral of e to the atx. I shouldn't say that. Qx, which we had in the linear case. And then by separating out those two parts, right, that's just the norm of q of x. Or actually, in our case, the norm of qzd of x, which is a squared norm, which is obviously positive because any square is positive. Right? So if you can write this Lyapunov function in this way, you can conclude that v of x is greater than or equal to 0 for all x, and a valid Lyapunov function. Or I should say this is a valid candidate Lyapunov function. Because candidate Lyapunov functions don't necessarily have the negativity, right? They're proposed Lyapunov functions is what do you think of them as? Yeah. So we call these, we have a specific name for these and a specific notation for this class of positive functions. So it's a class of positive functions. It's not the class of positive functions because there may be positive functions which don't look like this, but it's a class of positive functions. And we refer to this specific class of positive functions, change my color, as sum of squares polynomials. Or sum of squares functions, because actually z doesn't necessarily be monomials, but when we talk about sum of squares, we're referring to sum of squares of polynomials. And actually, we have a very specific notation for this class of positive functions with a sigma s for sum of squares. Sum, and this stands for squares. So we'll use that notation. Now, this is not all positive polynomials or all positive functions, but it is a class of positive functions, and it's a positive class we can parameterize, and in fact, in part C, we'll show we can optimize over it. Right? So it's an LMI condition. We haven't shown that yet. We'll show that in part C. But it is we'll show that it's an optimization problem. It is an LMI. It can be enforced using LMI constraints. So let's think about the question now more broadly of how hard it is. What do these sums? Why do we call it sum of squares anyway? So we'll talk about that in a second. So how hard is it to prove positivity of polynomials? Is sum of squares sufficient? Right? How close is the set of sum of squares of polynomials to all positive polynomials? Oh, sorry, I went over polynomials. Okay, so let's take a step back, right? What is the class of all positive polynomials, right? So this is definition. The class of all positive polynomials, right, is a set of polynomials, which are positive. Not particularly surprising notation, but that's what it is. We say a polynomial is positive semi-definite as opposed to positive definite. That's a harder problem. If the polynomial is positive, semi-definite, for all x, right? That's one of those constraints forms that we had. Of course, we talked about this problem is NP hard, but we'll come back to that. And so the question of how to enforce the constraint of a polynomial being positive for all x. Right? So how does one even test this, right? Or how does one even prove such a thing, that a polynomial is positive for all x? Now, that is... All right, sorry for that brief interruption. Hopefully I'll be able to merge these videos together. So as I was saying, the question of how close sum of squares is to the set of all positive polynomials, which we've defined here, comes back to a way of, so sum of squares is a way of proving that a polynomial is positivity. So it's a sufficient condition. And the question is how close that is to necessity. So can any proof of positivity, for example, be expressed as a sum of squares condition? Now that's a challenging question. So as a proof of positivity, So the question of proving things as positive is actually much harder than the question of checking whether an individual point is positive, of course. Right? So how do you tell if a polynomial is positive in general? Well, obviously, proving that it's not positive in general is quite easy, right? You just have a counterexample. You say if f of x is negative at some particular point, well, then it can't be positive everywhere. So that's a certificate of infeasibility, right? So that's easy, a proof of infeasibility, proof of not positivity. But the question of how to construct proofs of positivity is a question actually that's been studied in some great depth. And sum of squares is one of those techniques for constructing proofs of positivity. But of course, it's not the only one. Okay. So let's then think about what kinds of proofs of positivity we could just imagine, right? What are all the how do we prove that a function is positive? Well, like I said, any square is positive, so any squared function is positive, right? So that's good. A sum of squares is positive because if you add multiple positive things together, you get something which is positive. Right? G1, any G1, if it's squared, it's positive. Add another G2 squared to it, it's also positive. So if you sum up squares, you're positive, right? And that's SOS right there. But we could go a little bit further, right? Because other things are positive, right? Like if you take two positive functions and you multiply them together, that's also positive. Right? Because positive times the positive is positive. So positive semi-definite anyway. So that's a third way of constructing positive polynomials. And then even more troubling is there's a fourth way, right, in that if you divide a polynomial by a squared polynomial, that's also positive semi-definite because if 1 over a positive number is a positive number, you multiply a positive number by a positive number, it's positive. So positive divided by a positive is positive, right? So ratios of squared polynomials are positive, right? And this is getting beyond SOS. So we've now shown that there are lots of ways, and probably this list is not exhaustive. Maybe is this it? We have 4 ways now of proving polynomials are positive. Is that all? Are there other ways you can think of that aren't just combinations of these? So in general, right, one way of searching for positive, which combines all of these positive polynomials, is to search for for products of ratios of sums of squares of polynomials. And of course, sums of squares are positive. Divide positive by a positive, it's positive. Multiply positive by a positive, it's positive. Right? So this combines all 4 of these methods, M1, M2, M3, and M4. Right? But is that all? Is that enough? Is any positive semi-definite polynomial the sum product or ratio of squared polynomials? And it turns out this question is actually much older than optimization, obviously. It's one that's been studied for hundreds of years. It was actually listed under a very famous list of 23 then unsolved mathematical problems in 1900 by at the turn of the century by David Hilbert, famous from Hilbert spaces and so forth. So it has a very rich history. It's a very well studied problem. So of those 23 problems that were formulated, and honestly I can't remember the other 22, although on occasion I remember a few of them, but at this moment in time I can't actually name any of the other 22. But of those 23 problems, actually only 10 of them have been answered. So they're questions, right? And of those 23, we actually only have, in the intervening 120 years, only been able to answer 10 of them. Fortunately, the one we're interested in is the 17th problem, and that has been answered. Check. Give it a little plus. So specifically, that question was, using the original framework, and unfortunately it was in English phrasing, given a multivariate polynomial, so okay, so far so good, that takes only non-negative values, so positive semi-definite, over the real, so x is real, and can it be represented as a sum of squares of rational functions? So sums of squares, actually that's not part of the question, it's sums of squares of rational functions, so including ratios as well. So a sum of squares polynomial, we already defined this, is is denoted P in sum of squares if it can be represented as a finite sum of squares of polynomial functions. And the GIs, of course, don't have to be polynomial, or don't have to be positive. And this is the notation we use for polynomials, which take real values in variable x. So as I said, this actual problem has been resolved. It was resolved actually way back in the day, almost 100 years ago, by Artin in 1927, who proved that any positive semidefinite polynomial is a sum, product, and ratio of squared polynomials. So answered in the affirmative. So there was a necessary and sufficient condition for a polynomial to be positive is if it has it can be represented as the ratio of two polynomials, each of which are sum of squares. So that tells us that if we exhaust all possible representations as sum of squares polynomials, and we can't find a representation for that particular polynomial, then we know that it's not globally positive. So it's a necessary and sufficient condition. Okay. This was actually refined a little bit, and I forget who did the refining. It might have been Chu. But it was refined a bit actually later on. I forget, I think it was in the 50s. I'll put a question mark next to that. Where if the polynomial is definite, positive definite, that means greater than some positive constant epsilon, which is greater than 0, then actually we can assume that the squares on the bottom have a very specific structure. So specifically, we can assume that they're just the sums of the squares of the individual variables to some power d. So sums of squares to the power d, which is obviously also sum of squares. That is a necessary and sufficient condition for strict positive definiteness. And now this is it's still a sufficient condition for positive definite, but it's only necessary in the definite case, is that the sum of these xi squareds to the power d for some d times the polynomial itself is sum of squares. Right? So remember what sum of squares means. It can be represented as zd of x transpose p zd of x. So this is then a LMI, well, we'll show this in LMI, in a positive matrix P for positivity of a polynomial. Now, we don't have a bound on the degree d, so it's not necessary and sufficient. But of course, if you increase the degree, the test becomes more accurate. And in fact, actually, for our purposes, we'll almost always choose d equal to 1. Which is very accurate, but not necessary and sufficient. If this doesn't work, say, for example, if you're trying to prove positivity of a polynomial and you're not finding a sum of squares representation, then you can just add the sum of xi squared to it sequentially until you actually get a sum of squares representation. You know, for some, if you do that a sufficient number of times, then that's a necessary and sufficient condition. So of course, now this doesn't really answer the question of how we actually find these SOS representations. How is this an LMI? So partly I'll answer that in this lecture and give some more intuition, and partly I'll answer it in the next lecture where we actually code it into, or we talk about solvers for solving these things. Right, so to begin that process, we talked about the linear representation of the polynomials. And in this one, in this slide, we have to start by considering another possible way to represent polynomials. So if you remember, the linear parameterization of polynomials is achieved by p of x equals c transpose zd of x, which was linear in our in our decision variables, and also linear in the the monomials, ZD. Actually, our quadratic representation is still going to be linear in our decision variables, M, but it's called quadratic because it has the ZD on the left and the right. So it's quadratic in ZD of X. So quadratic in the independent variables. And of course, if we don't have any decision variables, right, then the quadratic name makes a little bit more sense. Yeah. So any polynomial of degree, say, 2D can be represented in a quadratic form, where you just take all the monomials of degree D or less. Right? There exists a quadratic representation with ZD of X. Right? So we drop the degree down to ZD. Right? So now, okay, let's look at that question, right? So if we parameterize the quadratic representations, then they look like this, right? So I've truncated a bunch of the monomials here, so there's some more, but just because it doesn't fit on the slide, I've stopped it after a certain distance. This is actually homogeneous polynomials, so it's a slightly different question. But in any case, my point here is that, so let's look at this quadratic representation, right? So these are the options you have for the representation, all these m's, there are 6 of them. And if you multiply this out, and this is important, right? Well, okay, x squared times x squared comes here, right? That comes down here. X squared times xy, that comes down here. Of course, the converse xy times x squared also comes down here. So there's a 2 factor there. Now we got the x squared times y squared, right? X squared, y squared. That term comes down here. Importantly, however, also xy times xy also equals x squared, y squared. So actually this term also comes down here into the same monomial, and that's an issue. The other ones, of course, we've got xy times y squared. That's here. So m5 comes down here. And m6 comes down here. And there's 2 of these, so we get the 2 factor there. But what this says, though, is that if you're looking for a quadratic representation of your polynomial, and you know what it is, say you know what your polynomial is, right? It's got a 7 here, right? This equals 7. What this means is that there's more than one quadratic representation of that polynomial. So for example, right, if we're looking for a quadratic representation of this polynomial, right, we write down the left-hand side here, we write down the right-hand side here, and we equate coefficients, right? This is a necessary insufficient condition for equality, that this coefficient has to be this one. 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 So the quadratic representation up till now is uniquely defined, right? We need m1 equals 4, m2 equals 2, m5 equals 1, or negative 1, m6 equals 10. But now what does m3 and m4 equal? Well, we have some flexibility now. So that has to equal 7. But of course, we have one constraint, and 2 variables here, 2 variables. So there's going to be underdetermined problem. There's going to be an infinite number of solutions to this quadratic representation, an infinite number of quadratic representations of the given polynomial. And this is good and it's bad, right? It's bad in that we can't just write down the quadratic representation and test if m is positive. But it's good in that we can search for one, right? We have a little bit of flexibility. So if our initial quadratic representation doesn't satisfy positivity, we can search for one that does. Right? So let's go back to that polynomial we had on the previous slide, right? So again, we equate these coefficients. We have 1, 2, 3, 4 constraints, which are give us 4 variables right away, M1, M2, M5, and M6. And then we have this constraint, the undetermined part, where we have 2 variables and 1 constraint. So overall, we have 6 variables and 5 equations. So we can actually parameterize the set of all possible quadratic representations by actually putting in that uncertain parameter here, lambda, right, where we have that flexibility. Right. Notice there were no other constraints on M3 here, for example. So which one do we use, right? Well, that's the question. So our goal is to search for a representation which is sum of squares, right? Right? Does there exist a lambda such that m is greater than or equal to 0? And if so, right, that means P is sum of squares, which we denote P in sigma s. So let's look at this sum of squares representation one more time, right? If we can find such a positive matrix, right, then again, right, if we can find a positive matrix m greater than 0 such that P has this quadratic representation in M, right, then again M has a square root, and so we can take that square root and write down a vector square, right? So actually really I should do P transpose P here, do that. So that equals G of x transpose G of x, where G of x is equal to P Z D of x, right? And actually, if we write this down explicitly, right, in terms of the matrix P, right, then this is equal to the sum of over I of Gi of x squareds, right? So this is equal to, right, G1 of x down to Gn of x, right? So it's a vector of polynomials. And so when we take the square, right, we square of each of them, and so that's equal to, right, Gix squared. Now, what are each of those Gi's? Well, those are just these, the row of the P, this P1 down to Pn times ZD. Right. So this is here row multiplication. So Pi Z D of x. That's what that is, which is equal to Gi of x. Okay. And so now we have a sum of squares, the Gi's, sum of our I, Gi of x squared. So it's sum of squares of a representation. So we now have a matrix inequality, which of course enforces the sum of squares constraint. Now, this again is a sufficient condition, and sum of squares itself is a sufficient condition right now because we don't have the ratio of sum of squares. But actually this part is necessary, it turns out. It turns out the existence of a quadratic representation with a positive matrix M is actually necessary and sufficient condition for P to be sum of squares. Okay. And actually the proof of that is relatively straightforward. Right, to show that any sum of squares polynomial has a quadratic representation with a positive matrix, right? It's really quite simple to prove, right? We just say, well, if P has a sum of squares representation, then I can write it down as a sum of squares of polynomials, Gi, for some polynomials Gi. Polynomials, right? Where presumably if P has degree 2D, then the GIs will have degree D, right? Because you're squaring them, so it can't have higher degree than that. So then each of these polynomials, because they're degree D or less, can be represented using the linear representation. Right? And then if we take this square term and bring it down here and then plug in this formula for G, right, we get this is equal to ZD, right? This is GI, and this is also GI because it's scalar. You can take its transpose. Right? And so, actually, there's a transpose there as well. So the sum over GI times GI. And then now what we've got here is this quadratic representation where you have ZD on the left and ZD on the right. So it's the sum of a bunch of these squared representations, but ZD doesn't depend on I, so we can take it outside the summation or bring the summation inside. And so we get, again, right, sorry, ZD of X transpose, the sum of these CI transpose CI transpose matrices. So these are all, remember, the CIs are vectors, right, because it's a linear representation. But when you take a vector and you multiply it by its transpose, you get a matrix, a rank 1 matrix. But that matrix is positive semi-definite. Right. Now now we sum up a bunch of positive matrices, and of course we know that the sum of positive matrices is necessarily positive. And so if we take the sum of those CI transposes, then we get a positive matrix Q, positive semi-definite, where of course the more of these CIs we add, the higher the rank of Q. However, the size of Q doesn't change, right, because it's fixed by Z. And so it can never be higher than, the rank can never be higher than full rank, right? I mean, you can't have a matrix which is higher rank than the dimension of the space, right? So it saturates at some point, and then you can represent it as a single matrix Q with inside in that quadratic representation. So this shows that not only is the LMI for sum of squares sufficient, but it's also necessary. If M is a polynomial of degree 2D, then M is sum of squares if and only if there exists a positive matrix Q, right, such that M is equal to the quadratic representation using Q. Right? And this whole thing is a quadratic representation. Right? So that takes us to the point where we have a necessary sufficient condition for sum of squaresedness of a polynomial, which is a sufficient condition for positivity of the polynomial. And now in the next part C of this lecture, we're going to talk about how to code these up into enforceable LMI conditions, because right now they have X in there, right? That independent variable, which is parameterized. And then, so in the next part of this lecture, we'll show how to get rid of those X's and put the whole thing in a finite dimensional form with just a bunch of linear equality constraints. And we'll talk about some solvers, some toolboxes, which allow you to do that relatively efficiently. Before I do that, however, I'll just give a brief example. So here's that polynomial. We formulate the constraints on this matrix M, right? Again, linear constraints on these variables, which are now M. M are the variables, decision variables. And we're searching for a positive M such that these 5 equality constraints are satisfied. 5 constraints. So clearly, right, positivity of this polynomial can be represented, or sum of squaresedness of this polynomial can be represented as an LMI, because I'm writing it down. Here's positive matrices, and here is the constraints on that matrix for a given polynomial. Now, in later lecture, in the next lecture, we'll talk about how to make this a variable itself, right? So these are coefficients, right? These are variables, right? What happens when we make these variables? Clearly, these are all variables. Variables, decision variables, that is, right? That's right. So we'll talk about how to enforce these constraints when these things are variables as well. But you can see already that this is going to come down to an LMI where x does not appear in this, or x and y do not appear in the LMI conditions, which is good because, right, MATLAB doesn't understand independent variables. This particular LMI is feasible, of course, and the positive matrix which enforces it is actually relatively simple. I can represent it using integers, which is convenient. We can find the square root of it using matrix, using MATLAB, P transpose P. And then, of course, if we're so inclined, we can construct that squared certificate by taking that square root, right, multiplying it out on the left and the right, to get these vectors, right? That's G. And then this is G1 squared, and this is G2 squared, right? So G2, G1, right? So a sum of squares representation derived using a positive matrix. Of course, in reality, we rarely pull this out and look at it because, well, that's not the point. But it is if you ever want to prove definitively that your sum of squares is a sum of squares and therefore positive, this gives a constructive way of doing so. All right. So now I will pause and come back in the next part of this to how actually we set up these LMIs in general when our polynomials are themselves decision variables. Stop briefly now.